Okay, so yeah, I was just saying that for tomorrow we'll do a review session, and so the only topic I have for today is to discuss about the symmetric matrices and the conic sections. Okay, so first, let me tell you something that is really useful about the transpose of a matrix. It is actually like the most important property of the transpose, but we haven't really had like a moment, like, you know, an opportunity to use it. But let me just tell you something about the transpose of A. So remember, like the transpose, like, you know, if like, for example, A is 1, 2, 3, 4, 5, 6. Right? A transpose is just changing the rows with the columns, right? So A transpose is like 1, 2, 3, 4, 5, 6. Or like you could also do this like for like a square matrix, like 2, 3, minus 1, 2. And so A transpose would be like 2, 3, minus 1, 2. Right? So the transpose is always just about changing rows with columns. Now, I mean, which is like a natural operation that makes sense to, like, you know, as a property you may want to use. But like the real application of the transpose, like the reason why it's useful, let me call that the key property. So the key property is that imagine that you have two vectors and the matrix. And A and the matrix A. So, you know, when you have two vectors, you can take their dot, I mean, assuming that they have the same length, size, you could take their dot product, right? You could take their dot product. But imagine that before taking their dot product, you multiply one of these vectors by A. Okay, so let me just put here like an A. So what this means is that I'm taking the vector V, I'm doing A times V, right? Like a matrix times a vector is a new vector. So this is a new vector, and then I'm taking the dot product of that new vector with U, okay? So it's just like before doing the dot product, multiply one of these factors by A. And the key property of the transpose, the property that makes it useful, is that this, the nice thing about the transpose is that you can kind of move the matrix A to the other factor of the dot product, but the price for moving it is to transpose it. So what I'm trying to say is that this is the same as a transpose of U dot V. So the property is that in a dot product, the matrix A can be moved between different factors as long as you transpose the matrix. Okay, so that is very, very useful. You'll see why in a second. So A can be moved to the other factor as long as you transpose it. Can be changed, can be moved to the other vector. Okay, so I mean, like that's not too bad. Like checking that this works, like it kind of, you can do it like a brute force approach that you just like literally compute both sides of the equation and you make sure that they coincide. Another way to do it is I literally, an alternative way is that you can actually define a transpose as a matrix. Yeah, you can define the transpose as the operation of a matrix that has this property, and then you just check that that agrees with like this thing about turning the rows into columns. So it's not something I want to like kind of spend verifying, but at least in the 2x2 case, you can kind of do it by brute force. Like you can, like for example, you can just this you can check this explicitly in the 2x2 case by doing like all multiplications. This can be checked. Okay, so why am I telling you this? Because like the first, like the thing that we have to talk about today is a little bit about symmetric matrices. So for today, like the discussion is about symmetric matrices. So what is going to be a symmetric matrix? These are also called self-adjoint, but I'll stick with calling them symmetric, also called self-adjoint. So I'll call them symmetric for now. These are going to be square matrices that equal their transpose. Okay, so a square matrix is a square matrix A is symmetric if it equals its transpose. So the equation for being symmetric is that A equals A transpose. And I think I have given you a couple of problems. I mean, there might have been on the PDFs one or two problems about like finding symmetric matrices. So this is, so if a matrix, the only way for a matrix to be equal to its transpose is for it to be square because you're changing the rows with the columns. So when you transpose a matrix, you change the size. So you need the two to be of the same size. So for example, I mean, in practice, it's not too easy to, not too difficult to check. Like, for example, like I could give you like 1, 2, 0, 3, and that one is not symmetric, right? Because a transpose is just 1, 2, 0, 3, which like wouldn't work. But something like 1, 2, 2, 3, that one is symmetric because A transpose is indistinguishable, right? So the point for a symmetric matrix is that you cannot differentiate it from its transpose. Like in fact, like what all the 2x2 symmetric matrices are pretty easy to describe, right? Because like imagine that A is A, B, C, D, right? What is A transpose? A transpose would be in general A, B, C, D, right? So if you look at it, if you want the two to agree, if you want these two to agree, this is already fine, this is already fine. The only thing that could be a problem is, that this number should match this number, right? So a symmetric matrix in the 2x2 case is just one where like the entries along outside the diagonal are the same. So the symmetric matrices, so this is like actually useful because for our purposes, we will only work with symmetric 2x2 matrices. So all 2x2 symmetric matrices are of the form A equals AB, BD. Okay, where A, B, and D are arbitrary. Is that making sense? Any questions about this up to now? So the 2x2 symmetric matrices are pretty easy to describe. Okay, and like it's actually kind of relatively easy also in the 3x3 case as well. It's just that again, we won't have too much use for them, so I won't. I'll kind of focus on 2x2 matrices for today. That's all that we need for our like the application that I had in mind. But you know, you could like still do say that they think similar things. Like for example, something like this. This one is not symmetric, right? But something like 1, 2, 0. Oops. If I'm correct, this one should be fine. This one is symmetric. So you say like it's like this a matrix being symmetric or not, it's not just something that you can discuss in the 2x2 case. But for today, I'll focus in that case because it's the one that I need. But you can still discuss this in more generality. Okay. And okay, so let me tell you why is this useful? What's nice about symmetric matrices? So here's the first important thing that you should know. It is the following. If you have two eigenvalues of A, which are different, then the corresponding eigenvectors are automatically perpendicular. Okay, so here's like fact one, and this is actually like a quick proof, so I'll tell you how it works. So if A is symmetric, if A equals A transpose, and lambda1, lambda2 are two different eigenvalues of A, and V1 and V2 are vectors, eigenvectors corresponding to lambda1, lambda2. Then V1 and V2 are automatically perpendicular or orthogonal. Then V1, V2 are automatically orthogonal. I'll put both words just to remind you that they mean the same. And that's you'll see why that's nice in a moment, in a couple of minutes. But it's useful because that says that if you have two different eigenvalues, their eigenvectors, like in the symmetric case, they come out completely perpendicular to begin with. You don't have to do anything to them. So why is this true? Well, remember what does it mean for something to be an eigenvalue and eigenvector? You have that A V1 is lambda1 V1 and A V2 is lambda2 V2, right? That's what it means to say that V1 and V2 are eigenvectors, right? Now, because at least since these eigenvalues are different, at least one of them is not 0, right? So since lambda1, lambda2 are different, at least one of them is not 0. I mean, you can suppose like, let's assume that lambda one is non-zero, just like it's the same. For example, uh, let's say lambda one is non-zero. Why is that useful? Because then I can just say that if lambda one is not zero, then I can divide that equation for by lambda one, and so I can kind of solve for v1 in this equation. Okay. It seems silly, but you'll see it's useful in a moment. Let's call this equation 2. Okay, and so what do I want to do now? How can I check that v1 and v2 are perpendicular? I need to check that the dot product is 0. So I need to check v1 dot v2 equals 0. Right, that would tell me that they're perpendicular. This would mean that they're perpendicular. This would say they are perpendicular. Again, if you have two vectors and their dot product is 0, that means that the vectors are perpendicular. So what is the dot product between v1 and v2? Let's work it out. v1 dot v2. Well, now what I'm going to use, let me write it v2, v1 so that it just looks like, and it doesn't matter how you write it because like the dot product, it's like if I write it this way, then it will look identical to the formula that I'm about to use. But right, like remember the dot product, it doesn't matter in which order you write the factors. U dot v is the same as v dot u. So what is v2 dot v1? Okay, so v2 is just v2, but v1, I'm going to use equation 1. So if I use equation 1, I'll replace v1 with the following. I'll replace it with a v1 divided by lambda 1. Okay. It doesn't matter, like the constant, I mean, the constant like is in the denominator, but you can think about it as being, just dividing v1 or dividing the a times v1. It doesn't matter because the constant, you can kind of put it like anywhere you want, as long as it's in the denominator. So it just looks a little bit better if you write it this way, because if you write it this way, what can you use? If you write it that way, you can use the key property of the transpose of, right, which the key property said that if you have a dot product and the matrix A is multiplying a vector, then you can move this matrix to the other side, to the other factor, at the expense of putting a transpose. So let me just use now the key property of A transpose. So what the key property says is that you can move this factor to the other side if you write it as a transpose. So let me put this A transpose V2 dot V1 over lambda 1. Okay. So again, that's why this is useful, because you can just move the matrix to the other factor. And why is that beneficial? Because A is symmetric, so A equals its transpose. Right, remember A equals A transpose by assumption because it's symmetric. So this actually gives you A V2 dot V1 over lambda 1. Okay. But now what is A times V2? A times V2, this is like an eigenvector, so that's just lambda 2 V2. And so this is like, now I'm going to use equation 2, so this is lambda 2 V2 dot V1 over V lambda 1. And the thing, like when you're taking a dot product, is that the constants, like you can take them out of the dot product. So like all of these so far is the same as v2 dot v1. So v2 dot v1 equals this, v2 dot v1 equals this, v2 dot v1 equals this, v2 dot v1 now equals this, which is lambda 2 over lambda 1. V2 dot v1. Which may not be so clear why this is useful, but notice that now you have the same factor on both sides of the equation, right? So if you want, you can write it like this. If you move everything to one side, you can factor it out. So you can write something like this. Right, like I'm just factorizing like v2. I'm moving this to this side, to the left side, and then I'm factorizing v2 dot v1. And so now you say, well, what is the product of two numbers? Like remember, this is a number. This is a number, and the dot product is a number also. And that's also useful to remember. The dot product is a number. So when is the dot product of when is the product of two numbers equal to 0? Either this factor is 0 or this factor is 0. So either 1 minus lambda 2 over lambda 1 equals 0, which cannot happen because lambda 1 is not lambda 2, right? There are different eigenvalues, which can't happen since lambda 2 equals different lambda 1. So that forces v2 dot v1 to be 0. So this, since this factor is never 0, that forces this one to be 0, or v2 dot v1 equals 0. And this must be, and this is the only possibility. Okay. So again, you'll see, I'm about to use this like in 10 minutes, 15. But it is, what's convenient about this is that it tells you that for symmetric matrices, the moment you have eigenvectors corresponding to different eigenvalues, they're automatically perpendicular. So if you remember like the Graph-Schmidt method, which was to turn vectors into perpendicular vectors, orthogonal vectors, like kind of in this case, is in a sense almost not needed, at least when the eigenvectors correspond to different eigenvalues, because like they already come perpendicular. You don't have to do anything to like kind of fix them. Okay. So it's not like again, it's not like it is a clever proof. It's not too bad, but you kind of have to. It does require a little bit of it does require some tricks to have thought about like solving like this equation in this way. But it's like a fun argument to just illustrate why it's useful to have this property that you can move the matrix to the other factor in a dot product. Okay, is that okay? Any questions about this? So far so good. Okay, so now this actually, by the way, this works. This proof that I gave works for a matrix that's symmetric of any size. But for now, let me just focus on the 2x2 case. Okay, so now just all that I'm about to say will be true in the will be specific to the 2x2 case. I mean, some things also work in more generality, but In the 2x2 case, it's just what I need. So let's just talk a little bit about 2x2 symmetric matrices. So again, I told you that they look like A, B, B, D, right? Like the only restriction for being a symmetric matrix in the 2x2 case is that this entry must equal this entry, right? Everything else is allowed. So in this case, you can actually compute the eigenvalues pretty explicitly. So it's like a nice formula for the eigenvalues. So what are the eigenvalues of A? Well, if you remember, the eigenvalue equation is determinant of A minus lambda I equals 0, right? What is A minus lambda I? That's the determinant of A minus lambda B, B, D minus lambda, right? So that has to be equal to 0. So what is this determinant? Is A minus lambda times D minus lambda minus B squared equals 0. Okay? And now let me just rewrite this a little bit. It is AD minus A lambda minus lambda D plus lambda squared minus B squared equals 0. Okay? So let me just rearrange the terms according to their lambdas, increasing orders of lambda. So the lambda square is the first one. And then let me put it minus A plus D lambda plus AD minus B squared equals 0. Right, so this is kind of like the quadratic part. I mean, this is like, usually this quadratic equations is with x instead of lambda. So this would be like x squared, this would be x, and this would be like the term that's just constant, right? So think of this as a quadratic equation. Is that making sense? I don't know if you remember, like there was this formula for the quadratic equation for x, which was that x equals minus b plus minus square root of b squared minus 4ac over 2a, right? That was a solution of a general quadratic equation. Here, it is the same. You just have to be a little bit more careful because like the names of these coefficients are, you have to adjust this formula to these numbers. But using the formula for the solutions or the roots of a quadratic, right? You can find that lambda, there are like two the eigenvalues would be like one eigenvalue is with plus and the other one is with minus, right? So one solution would be minus b, but here b is all of this, right? So you get a plus d. Let's make this one with the plus, so you get b squared. Again, b squared means square this, so this is a plus d squared minus 4 ac. A is 1 and c is all of this. All of this is being divided by 2. And the second eigenvalue is lambda 2, which is it's the same. The only difference is that there's like a minus here, right? So let me put it like this. Is that making sense? Are there any questions about this? So this is actually a pretty explicit formula for the eigenvalues. It's just that it can be simplified even a little bit better. It's still not in its best form, in its best shape. To simplify it a little bit better, I have to work out what is inside the square root. So what's inside the square root? you have a plus d squared. By the way, I'm not expecting anyone to remember this formula. I mean, in practice, once the matrix has specific coefficients, you can always find the eigenvalues more easily, solving the equation. I'm just saying, like, by writing it this way, you'll see that, like, there's something you can notice that it would have been hard to notice, like if you just like do it like with specific numbers. So this is a squared plus 2ad plus d squared, and then this one gives you minus 4ad plus b squared, right? So I'm just expanding everything out. Okay. And so you get, like these, you can combine it. So you get a squared minus 2ad plus d squared plus 4b squared. And this gives you a minus d squared plus 4b squared. Okay, so this looks a little bit nicer. So that actually tells you that the first eigenvalue is a plus d plus the square root of this thing over 2. And the second eigenvalue is a plus d. Remember, it's just the only difference is that there was a minus sign here. And then this is okay. So this is a formula for the first eigenvalue. And this is a formula for the second eigenvalue. So here are like the two things to note. Like, why am I putting the formulas so explicitly? Because there are two things to notice. So why is it useful to have like this explicit formula? So here are two basic observations. The first one is that this thing inside the square root is always non-negative, right? So what that means is that here you always, when you take the square root, you never have like a situation where you're taking the square root like of, this imaginary number. So like the square root of -1 or things like that. So you don't need so the square root will always be a real number in the sense that always be a real number in the sense that no square roots of -1 will appear. So, I mean, I don't know if you worked out one of the problems on the assignment, and I think I've done some examples before as well. Like sometimes when you compute eigenvalues, like the square root of -1 shows up. I'm just saying that in the symmetric case, that never happens because when you take the square root here, this is always non-negative. So that's convenient. That's actually useful. So that's the first observation. And the other one is also very nice. So, I mean, if you remember when you're solving a quadratic equation, it is not impossible for these two numbers to agree, right? By the way, this quantity was called the discriminant. If you remember your high school job, like I don't remember when you see this for the first time, but maybe in high school. So this quantity b squared minus 4ac is called the discriminant. So lambda1 can be equal to lambda2, but for that to happen, the stuff inside the discriminant must be 0. Only when a d squared plus b squared 4b squared equals 0. But here's the thing: each of these numbers, because it's a square, right, is a non-negative number, right? Each summand is non-negative, since each summand is non-negative. This needs. How can the sum of two non-negative numbers be equal to 0? What that forces each number to be each summand to be 0 as well. So you need we need each of them to be 0. So you need a minus d squared to be 0, and you need 4b squared to be 0, which forces a equals d and b equals 0. So that's nice, because remember, what was the matrix A? A was A, B, B, D. So in this case, A equals D, right? So you can replace D with A. So, and B equals 0, right? So that means that in the symmetric case, you only, this is a multiple of the identity. You can write it as A times 1, 0, 0, 1 if you prefer. That doesn't matter too much. But what this is saying is that in the symmetric case, the only way in the symmetric case for the eigenvalues to be repeated is if the matrix is a multiple of the identity. So for a symmetric matrix, the eigenvalues can be repeated only when it is a multiple of the identity. The eigenvalues are the same. Only when A is a multiple of the identity. Okay. So that's not too interesting, right? That's not too interesting because, like, we understand very well the multiples of the identity. So for the remaining part of today's class, I will just assume from now on, I will assume that lambda 1 is different from lambda 2. So and like for all the applications that I have in mind, that will be also true, because like as you just saw, when the eigenvalues are repeated, this is not too useful. I mean, it's not too interesting. So from now on, I will assume that lambda 1 is different from lambda 2. So what does that mean? It means that you have two different eigenvalues. Each of them will have their eigenvector, right? So you have two different eigenvalues. Lambda 1, lambda 2, with eigenvectors v1, v2. Well, and what happened, right? What happens if you have a symmetric matrix with different eigenvalues? This is what we discussed a couple minutes ago, right? If you have a symmetric matrix with different eigenvalues, if A is symmetric and the eigenvalues are different, then the eigenvectors are perpendicular. So every 2 by 2 symmetric matrix looks something like this. You can draw like, so V2, V1 are perpendicular. Why? So in the 2 by 2 case, you can always think about it in the following way. I mean, just to make the picture somehow nice. Like you can say, well, maybe this is the first eigenvector. I don't know where it is. Let me just draw it on the first quadrant for simplicity. Doesn't matter where you draw the first eigenvector. Like the second eigenvector has to be perpendicular to this one, right? Has to be at a 90 angle degree. So it will always look like this. Is that making sense? So these will, I mean, it could also look like this. It could also look like this, but you know, like the eigenvectors, you can multiply them by a number, and like you know, if v is an eigenvector, 2v is an eigenvector, minus v is an eigenvector, so it's not too difficult to arrange it so that it looks like this. Um, the important thing to have in mind is in this picture is that you can make them. The important thing in this picture is that they have like 90 degrees. So in fact, and let me just put them like this. Because like the eigenvectors may not necessarily have the same size. What's important is that their angle is 90 degrees. Okay, but now you know you can rescale the eigenvectors so that they have like unit length. Um, that you can always do. You know, you can always rescale the eigenvector. You just divide by its length. So how does this look now? Now, I mean, I'm just making them of the same size. Okay, and so this is nice because what happens now, if you call theta the angle between, remember on the x and y axis, there's always these two vectors which are called E1 and E2. I don't know if you remember our friends. So here's E1, which was 1, 0, and here's E2, which is 0, 1. Okay. So what does this mean in the picture? Let me, yeah, this is a little bit overcrowded, but let me just put them, I have to make them of the same length also. Well, let's say that theta is the angle between V1 and E1 in this picture, right? Okay. Uh, so what do you think is happening here? If you remember, this is the first thing I started on the first day of class, right? We had the rotation matrix. Right. So uh, what do you think happens if I rotate according to this picture, what should I get if I rotate the vector E1 by theta degrees counterclockwise? If you take this vector and rotate it by theta, what vector should you get according to this picture? What do you think? If you rotate it by an angle of theta? Well, you get V1, right? Like what this means literally is that if you rotate E1 by theta, you are getting to V1. So this should be V1. And if you rotate E2 by theta, you will get to V2. So, but this is kind of nice because what is this thing? This is cosine of theta minus sine of theta, sine of theta, cosine of theta. And what is E1 is 1, 0. So this is actually going to give us a formula for V1 and V2. And this is cosine of theta minus sine of theta, sine of theta, cosine of theta, V2, which this is 1, 0. This is V2. So this is if you do this dot product, this multiplication, that's the cosine of theta. V1 is cosine of theta, sine of theta, and V2 is minus sine of theta, cosine of theta. Okay. So let me write that down because so we just found something very useful. Like let me write it down more like as a theorem or result. So this is like an important result, like so important. So what that means is that if A is symmetric, if A is 2 by 2 and symmetric, A equals A transpose, and lambda 1 is different from lambda 2, and lambda 1 is different from lambda 2, the eigenvalues are different. Then one can write one of the eigenvectors can be written as cosine of theta, sine of theta. Then one of the eigenvectors can be written as V1 and the other one. And the other one has for some angle theta. For some angle or rotation theta. Why is that useful? Because I don't know if you remember, we talked about diagonalizing a matrix, right? Remember when A was diagonalizable, right? Moreover, A is diagonalizable. What did A being diagonalizable meant? It meant that A was Q inverse, right? Where Q was a matrix of eigenvectors. And D was a matrix of eigenvalues, right? So here D is a matrix of eigenvalues. So D was like lambda 1, 0, 0, lambda 2. But what is Q? Q was like a matrix whose first column was the first eigenvector. A matrix whose second column was the second eigenvector. But if you write down what I just wrote, this is the first column is cosine of theta, sine of theta. And the second column is minus sine of theta, cosine of theta. So what that means is that in this, okay, and now I can tell you which is just precisely the rotation matrix, right? So this is like the rotation matrix. So here's like the most important thing of what I have said today, that in the symmetric case, you can diagonalize a matrix using a rotation. So here it is. When asymmetric, you can diagonalize A using a rotation. So you can write this as A, and here's like, this is like the important formula of today. You can say that A equals R D. So here you would have to put like the inverse, like the things like the inverse of a rotation matrix is the transpose. Like that's easy to check. So all that I have said, like the point of everything that I have done so far today is just to say that in the symmetric case, the diagonalization can be done using a rotation matrix, which you'll see in a second, but that's very useful. Okay, so let me finally tell you why we are doing all of this. So let's talk about conic sets. conic sections. It's a very nice topic, I think, and a surprising application, maybe of linear algebra. Let's talk about this. Let's see if I can go to GeoGebra quickly. Okay, let me share GeoGebra. Oops. So, what is by conic section? I just mean like an ellipse or a hyperbola. So here's like, for example, the equation of an ellipse. Okay, that looks like an ellipse. It's 5x squared plus 8 y squared equals 36. You know, the only reason, like the easiest way to recognize this is an ellipse is that you say, well, it is like a sum of squares, right? So just in analogy with a circle was like x squared plus y squared, basically. So an ellipse should be something like that, but like instead of like x squared and y squared being alone, they're maybe multiplied by a number. And something like this could be like a hyperbola, okay? So like at least in this case, like the difference like here is that for the ellipse, both variables have the same sign. And for the hyperbola, one they have opposite signs, meaning that one is positive, one is positive and the other has negative coefficient. Depending on how where the negative coefficient is being placed, the hyperbola will open, will expand in different directions. Okay, but so that's more or less okay. The question is like, for example, okay, let's go back to the ellipse. So imagine I had given you something like 5x squared plus 8y squared. We already know that that was an ellipse. Imagine that I had introduced a term that is, minus 4xy. So I'm going to put the same, but now in the middle, I'm going to put what I call like a mixed term. So something involving x and y. Okay, so it is like a very similar equation. If you notice, like the only difference is that, I change, I introduce this thing that involves x and y. And I may ask you, and here, I'm showing you it's an ellipse, but like the first thing to notice is that it's kind of like an ellipse where, it seems like it has been rotated a little bit, right? It doesn't seem like perfectly aligned with the x and y axis. So the first thing you could ask is first, like, how do I know that it's an ellipse if I didn't have GeoGebra, right? Because like it's not, you shouldn't think that it's just like, oh, because like the squares are still positive coefficients and that should be an ellipse. It's more complicated than that. So if I had just written the equation, how would I identify this as an ellipse? And second, how do I identify this as, how can I identify the angle of rotation where like, I would like, to see like this, the ellipse straighten out. And similarly, imagine I had changed one of the coefficients here. If I change one of the coefficients here, like I still have an ellipse. Sorry, now I have a hyperbola, but you see, like you kind of have to twist your head a little bit to identify it. So I'm just saying that when there's like a term that's like a mixed term, like identifying the equation as a hyperbola or an ellipse is a little bit more tricky. Like just to give you a different one. Yeah, let's just do this one. For example, if I had written something like x squared equals 4, I mean, that's very easy, right? X squared equals 4 is two vertical lines. But now notice that the effect of like, introducing a mixed term. So let's put 2 square root of 2 times x, y. Okay. So if I introduce something that depends on x and y, I change from a line to lines to a hyperbola. So what we will try to figure out right now is kind of how can you tell? Oh, this is a good example because here both coefficients are positive, right? So it's not that because both coefficients were positive, that you should get like an ellipse. Here you're still getting a hyperbola. So it is a bit more tricky. So like what I'll show you is like a cool trick to identify what you should get using eigenvalues. And symmetric matrices. So that's like kind of like the last application I had in mind for the course. I'll definitely ask you one on the exam where I give you like an equation of a hyperbola or an ellipse, and you have to identify it. Like it's like a very classical problem. So it will be essentially like the one that I'm like the examples I'm about to do, but just with different numbers. Like everything else will be exactly the same. Oh, just give me a second. Can you still hear me? I just think I need to plug in my iPad to. Ah, here it is. Sorry, you can still hear me, right? I said I wasn't. I think the iPad was like giving me some issues, so I wasn't sure. Um, so right, like for us, conic sections would be either ellipses or hyperbolas. I mean, parabolas are also included in the definition of a conic section, but we won't worry about those. Okay, so here's the thing. The equation of an ellipse, is, or a hyperbola is going to be something like this: ax squared plus bxy plus cx squared equals t, or let me call it e, because otherwise you may get confused. I mean, well, okay. It won't be as bad, I promise. So the equation is where A, B, C, D, where A or B or C is non-zero. Okay, so the equations we're going to look like at are these equations. Now the cool thing about, so examples of these equations would be like the ones that I just wrote. Like 5x squared minus 4xy plus 8y squared equals 36, or x squared minus 2 root of 2xy equals 4, for example. So an equation for a conic section looks like this. Okay, and then the idea is, the cool thing is that you can rewrite this equation using matrices. Can be rewritten as xy times a b over 2 b over 2 c xy equals d. Okay. So let's just check that works quickly. So y because well, to multiply this, you can multiply. I mean, this is like a multiplication of three. You can think of this as a multiplication of three matrices. So let's do this one first. This will give you xy. What is that going to be? This is going to be a vector, right? The first entry is going to be ax plus by over 2. And the second entry is going to be b over 2x plus cy equals z. And then when you do that, when you multiply these two vectors together, you get, ax squared plus bxy over 2 plus byx over 2 plus cy squared equals z. I mean, and then the two add up to these two in the middle add up. So you get ax squared plus bxy plus cy squared equals z. Okay, so what I'm saying is that for every equation that you had before, you can associate to it a matrix. Okay, so let me just do it for these two cases. It's very easy to identify the matrix. It's just literally copy paste the coefficients that you see here. But the one that's the mixed term gets divided by 2. So for example, what I'm saying is that this is like the same as xy 5 minus 2 minus 2, 8 times xy equals 36. So this goes here, this goes here, and this one kind of has to get split between the remaining two coefficients at the remaining two entries of the matrix. That's why it gets like half. You have to divide it by 2. Okay? It's always like the same. So, and the other one, which I had written down, which was x squared minus 2 root of x, xy equals 4, would become xy times 1 minus root of 2 minus root of 2, 0, xy equals 4. So again, it's similar. This one, there's a 1 here secretly, so you put a 1. There's a 0, there's no 0, I mean, there's no y squared, so you have to put a 0. And then the blue term is like in here because it gets divided by 2 again. Okay. Now, what's the nice thing? Is that making sense so far, so good? So what's the nice thing here? The nice thing is that the matrix that appears, the matrix that always appear in these problems is symmetric. So what's the important fact? Is symmetric. Okay. So we can apply the stuff that we have been discussing up to now. So let me tell you what's the two important things of the fact that this is symmetric. The first important fact is that, so this has two consequences, and you'll see why in a second when I do when I show you the examples. So the first consequence is that if the eigenvalues have the same sign, then the equation will be of an ellipse. So if the eigenvalues, you'll see why once I do the example. So if the eigenvalues lambda 1, lambda 2 are of the same sign, are both positive or both negative, then the equation will be an ellipse. If the eigenvalues are of opposite signs, then are of opposite signs, then the equation will be a hyperbola. Okay, so that's the first thing. The first thing is that the eigenvalues of the matrix will identify for you whether you've got an ellipse or a hyperbola. And the second important thing is that if you write the eigenvectors of A as a rotation matrix, and I will show you that in a second. If you write the eigenvectors of A as a rotation matrix, again, where this one like would be the first eigenvector, for example, and then this one would be the second eigenvector. Then if you rotate the xy axis by the angle theta, with respect to those new axes, the conic section will look standard, like meaning parallel to the axis. Then if you rotate the xy axis by this angle theta, the conic the conic equation will, or the conic the parabola ellipse will be standard. The ellipse parabola will be standard. The ellipse hyperbola, sorry. By standard, I just mean that it looks non-rotated. Like the axis, the symmetries are parallel to these lines. So it will look non-rotated. I'll show you what I mean once I do the. I'm about to do the examples for you, but like this is essentially what I'll ask you to find in these problems. I'll ask you to identify the equation as a hyperbola or an ellipse. That just requires you to do like the eigenvalue stuff. And then I will ask you to find the angle of rotation, because the angle of rotation is like what tells you how much you have to rotate the xy axis to get to this standard case. Mm-hmm. Okay. Just give me a second. Okay, so let me do it for these two examples that we have been discussing. So to show you how this looks like. So let's start with the first one, which is a little bit easy in terms of the algebra. So let's show examples. Let's start with this equation, which was x squared minus 2 root of 2 xy equals 0. Okay, so again, like the first thing you should do when you see this is just immediately write down the symmetric matrix. The symmetric matrix is 1, 0, minus root of 2, minus root of 2. So it's like, again, it's just copy paste the coefficients. Copy paste the coefficients. The one that's the mixed one gets divided by 2, and there's 0 y squared here, so that's why I'm putting a 0. That's how it looks like. And then the next step is to find the eigenvalues of A. So you have to look at the determinant of A minus lambda I equals 0. So this is the determinant of 1 minus lambda minus root of 2 minus root of 2 minus lambda equals 0. So this is what does this give you? Minus lambda plus lambda squared minus 2 equals 0, I believe. So it's lambda squared minus lambda minus 2 equals 0. And this is okay, this is lambda minus 2 times lambda plus 1 equals 0. So what are the eigenvalues? Eigenvalues are lambda equals 2 and lambda equals minus 1. Okay, so those are the two eigenvalues that you found. Since they are opposite signs, right? One is positive, the other is negative. This will be a hyperbola. Okay, since one is positive, the other negative, this equation will be a hyperbola. Okay, and then the only thing that's left to do is to find the eigenvectors for each of them. So let's find the eigenvector for lambda equals eigenvector for lambda equals 2. So now you have to look at A minus 2i. That is minus 1 minus root of 2. Let's see. Okay, and this, remember you have to look at the null space of this, so you can do minus root of 1, so you get 1, root of 2, minus root of 2, minus 2. And then, I mean, if you do root of 2, root 1 plus root 2, you get 1 root of 2, 0, 0. Right, so the equation is, the null space equation is just that x plus root of 2 y equals 0. So x is minus root of 2y. Right, so what is the eigenvector here? It's like xy would be minus root of 2y, y. So the eigenvector would be minus, I mean, it's y times minus root of 2, 1. Okay. So the eigenvector is this one. Minus root of 2, 1. But the only thing that's important in this case is that you must make it of length 1. So here it must be of length 1. We do for this application, we do need to normalize them. So what is the length of this vector? Well, it's remember each square each side, so it's the first entry square is 2, the second entry square is 1, is so root of 3. So the unit length eigenvector is actually minus root of 2 over root of 3, 1 over root of 3. Okay. So so it is the same usual eigenvector. It's just that you do have to make them of unit length in this for this application to work. That's important. And then what is the other one? Now we have the eigenvector for lambda equals -1. Well, that's a plus I in this case, right? So you get 2 minus root of 2 minus root of 2, 1. I mean, there are different ways to do it. Like you can put it like, it doesn't matter too much actually. Like you could, like in fact, the easiest thing to do in this problem is just to do, you could do root of 2, row 2 plus row 1. That's easiest to simplify this. Because you do that, you get 0. And so the null system is just minus root of 2x plus y equals 0. So y equals root of 2x. So xy is x root of 2x, which is x 1 root of 2. And then the length, again, this is not necessarily of length 1. So what is the length of this vector? What is the length of 1 over root of 2? Is like the square root of 1 plus 2. That's also square root of 3. So that the eigenvector that we want is the region of 1 divided by its length. So it's 1 over root of 3, root of 2 over root of 3. Okay, so what is so just to summarize this, like we had for like eigenvalue 2, like you can make a table. So for eigenvalue 2, the eigenvector was minus root of 2, 1. And for eigenvalue -1, the eigenvector was 1 over root of 3, root of 2 over root of 3. Okay. So if you do the dot product between these two vectors, you'll notice that it is 0, which makes sense because I have told you that whenever you do the dot product of in the symmetric case for distinct eigenvalues, the eigenvectors are perpendicular. So that's what it looks like. Okay, and now what I'm like, oops, I forgot to divide by. It's the purple one, right? So it's divided by minus root. This one is divided by because we want the one that is sorry about that. We want the one that has unit length. Okay, now the last part is the claim that these form the column of a rotation matrix. So these vectors are the columns of a rotation matrix. Vectors are the columns the rotation matrix for us is always cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay, so by comparison, right, you have to compare like the first, like, each vector with each column. So the easiest thing to do is kind of to, because none of these entries has like the minus sign. The easiest thing to do is to take this one as the first column, and then take this one as the second column because this one already comes with the minus sign. So what I'm saying is that you should take, but like by comparison, compare them. You should take this to be like this. And so, I mean, that already, by the way, yes, that's correct. Yes, you can, oops, if you prefer, you could write it as root of 2/3. Yes, that is true. So you could, if you compare the first coefficient, you get the cosine of theta is 1 over root of 3. And then if you compare the second coefficient, you get something. I mean, the thing is, like, this is not a special angle, so it's not that I would expect you to say the exact value for this angle. You can just say, for example, the theta equals arc cosine of 1 over root of 3. If you say that, that's more than enough. Like, I'll leave that as a correct answer. So you don't have to approximate it or anything. That just happens to be that if you enter that on your calculator or whatever, that is, I believe, like 55 degrees. But I mean, like, just this is enough, like, just like, that's enough. What's more important in terms of the picture, what I'm trying to say is that in terms of the picture is that you had xy, then you have this angle theta. You have to imagine that you rotated the x and y axis by this angle. So you have like v1 here, which is 1 over root of 3. And root of, if you prefer, we can write it as root of 2/3. And then you have the other one, which is at 90 degrees. And this is minus root of 2/3, 1 over root of 3. And with respect to kind of, you should, like, I mean, what happens in practice is that you think of this as like a new x-axis and new y-axis. So it's called like x prime, y prime. That I won't get into those details. The important thing is that with respect to this x-axis, y-axis, like the equation will look like a hyperbola that's parallel to these new lines. So I'll show you how this looks like in GeoGebra in a moment. But that's kind of like the picture that you should think in mind, that you kind of have to rotate the xy axis. You rotated the xy axis by this angle theta. And with respect to these eigenvectors, like the hyperbola is kind of aligned. So it gives you like, it looks like in the standard way. So let me see if I can show you that on GeoGebra. Okay, right. So like the equation was x squared minus 2 square root of 2 times xy equals 4. As I said, so that's the hyperbola. The fact that it's a hyperbola, you can determine just by the fact that the eigenvalues were of opposite signs. And then how do you find, like, my claim is that if you had like, you can define this vector. What were the entries of the eigenvectors? The entries were 1 over square root of 3, square root of 2/3. So this was 1. And okay, So one of the eigenvectors we found is this one, which is the one that I colored in green on the notes. Okay, this is the first one. And the other one was the purple one. So it was b equals minus square root of 2/3, 1 over square root of 3. It was this one. Okay, so again, I don't know how clear it is to, to, to see it like in this picture, but somehow it's easier just to think that you rotated your head so that you're looking at it like, like your head is kind of tilted so that your vision kind of aligns with these new vectors. But like the point is that with respect to these new vectors, like the hyperbola kind of looks standard in the sense that its symmetry is with respect to these axes, because with respect to the original x and y axis, it kind of looks like shifted. So there's two, like what is, one option would have been like imagine like, like you have a cell phone, like right now it's tilted with respect to the x and y axis. So one option is kind of to untilt it. One option is to literally tilt the cell phone, or you leave it like this, but you just tilt your head, right? So that's kind of what we're doing here. We're tilting our heads so that with respect to the tilted vision, like the hyperbola kind of looks standard. But like the idea is that it just follows from the eigenvalues and the eigenvectors from the symmetric matrix. Okay. And so this angle, if you were to compute this angle, it is like more or less like 55 degrees. So what I'm saying is that what I did is kind of rotate this vector by 55 roughly, and the other vector, which is 0. Oops, sorry, 0. And this other vector by 55. So each of these black vectors was rotated by 55 degrees, and that's how roughly, and that's how you get to the purple and green ones. Okay, so in fact, you could like give this like a different color. Oops. So it's a cute application. It shows you like, again, it's maybe like an unexpected application because, this is like a quadratic equation and linear algebra. All the equations were kind of linear, so you wouldn't maybe expect it to be useful for something quadratic. Okay. Let me do the other one in the remaining time that I have, the other example that I had written earlier. Here's another example. Well, in fact, I'll do it with slightly, well, let's give it like this. Okay. So let's say now I had given you this equation, plus 8y squared equals 36. So the matrix in this case is 5 minus 2 minus 2, 8. So what are the eigenvalues? You look at determinant of a minus lambda I. So this gives you how to set it equal to 0. So this is the determinant of what? 5 minus lambda minus 2 minus 2, 8 minus lambda equals 0. So it gives you 5 minus lambda times 8 minus lambda minus 4 equals 0. And this is what? This is lambda squared minus 13 lambda. plus 36 equals 0, I believe. And this is lambda minus 9 times lambda minus 4 equals 0. I mean, I'll always give you eigenvalues that can be factorized so that you don't have to use a quadratic formula if you can just like see how to factorize it, just to make it easier. But so the eigenvalues here are lambda equals 9 and lambda equals 4. So since there are two eigenvalues, right? The important thing is that they're of the same sign, right? They're both positive. So the equation will be of an ellipse. Okay. And then again, just find the eigenvectors. So what are the eigenvectors for lambda equals 9? It's a minus 9 times I. So this gives you minus 4, minus 2, minus 2, minus 1. Right, and then if you do like minus 2 row 2 plus row 1, yeah, you get 0, 0, minus 2, minus 1. From there, you can see the null space is like the equation is minus 2x minus y equals 0. So minus 2x equals y. So the eigenvector is what? X minus 2y. So that's the first one. But again, what's the length? You must always rescale it. So the length is 1 plus 4, in this case, root of 5. So the eigenvector is not the one that we found. This is like just a rescaled version. So eigenvector is 1 over root of 5 minus 2 over root of 5. And okay, so that's the first one. And then the other eigenvalue was lambda equals 4. So we have to look at a minus 4i, which in this case it gives you minus 1, 1, minus 2, minus 2, 4. Okay, and here if you do just 2 row 1 plus row 2, you get 1 minus 2, 0, 0. And the equation is like x minus 2y equals 0, so x equals 2y. So the eigenvector is x, y equals 2y, y, which is y, 2, 1. And again, the length must be 1. So let's compute the length of this eigenvector. Is it's also 4 plus 1, so it's root of 5. And the eigenvector we work with is this one rescaled. So the eigenvector is 2 over root of 5, 1 over root of 5. Okay, so let's just summarize the situation. We have so one eigenvalue was lambda equals 1. Sorry, lambda equals 9. For that eigenvalue, I said the eigenvector was 1 over root of 5 minus 2 over root of 5. And the other eigenvalue was lambda equals 4, and the eigenvector was 2 over root of 5, 1 over root of 5. And again, these columns must be compared with the columns of the rotation matrix. So you must compare these with a rotation matrix. Cosine of theta minus sine of theta, sine of theta, cosine of theta. And again, the easiest way to, I mean, in this case, the easiest way to match them is just that, you can put this one at the first column, and you can put this one. Oops. Okay. This is more interesting. So, right, the first one is already matched. Okay. I like this example. So remember that an eigenvector, just to do the comparison, you can multiply an eigenvector by a number. So for example, if I multiply this eigenvector by -1, it's still the same eigenvector. I mean, it's still like an eigenvector that's allowed. Use -1 over root of 5, 2 over root of 5 instead. So you're allowed not only to rescale them, you're also allowed to multiply them by -1 if needed. So the advantage of doing that is that now this column matches, and this is a good example because of that. So this column matches this one. Okay. So not only are you allowed to rescale them so that they have length 1, if needed, you can multiply each entry by -1 so that the signs coincide. Okay, so the rotation matrix is going to be oops. So it's just like, yeah, when you compare the columns of the eigenvectors with the columns of the rotation matrix, just you can arrange them so that like it literally, the negative coefficient is like in the second entry. Basically, that's the goal. You can always set it up that way. So yeah, like the idea is always to have the negative coefficient in the second entry. And from there, it's the same. You have that cosine of theta equals 2 over root of 5, and sine of theta is 1 over root of 5. And so, I mean, again, this is not a special angle or anything, so it's not that I will expect you to simplify it further, except for saying that theta is, for example, the arc cosine of, I mean, you can also do it for sine, but like you can say that theta is, for example, the arc cosine of 2 over root of 5. Okay. So there's no more need to simplify that. Let's see how much that was. I can check that. What was the arc cosine of 2 over square root of 5? It's like it is like roughly like 27 degrees. In fact, we can see it. I'm about to show you this in GeoGebra so that you can see it for yourselves. But so you see, it's always identify the symmetric matrix. Once you have the symmetric matrix, find the eigenvalues. They'll tell you whether it's hyperbola or ellipse, and then find the eigenvectors of length 1 and match them with the rotation matrix to find the angle. So it's 3 steps: matrix, eigenvalues, and then the matching with the rotation matrix. So those are the 3 things that you need to do on these problems. So let me see if I can show you how this equation looks like. It was 5x squared minus 4xy plus 8y squared equals 36. Okay, so this is how this one looks like. And then the eigenvectors need to be changed a little bit. So the first one would be, now the first column was 2 over square root of 5. And then 1 over square root of 5. So that's the first one. And then the second one was minus 1 over square root of 5. And then 2 over square root of 5. Okay, so that's the second one. So let me just hide these two to not make it too confusing. So if you look at this, what I'm saying is that it is an ellipse. Again, that can always be determined just from the eigenvalues. And then the point that I'm making is that if you have rotated, if you have rotated the XY axis by 26 roughly like 27 degrees, or like if you prefer, you tilt your head by 27 degrees, then the ellipse kind of looks like completely parallel to this new, like the ellipse looks like if you think of this as an axis, and this is another axis, then the ellipse looks parallel with respect to the rotated axis. Okay. And I mean, again, that's actually useful. Doing this trick is useful in different situations. Like if you ever take multivariable calculus, the second derivative test to classify critical points is actually basically doing this, although they won't tell you that because multivariable doesn't have as a requisite linear algebra. But basically, when you have like a function of two variables, there's this thing called the Hessian matrix. And then the eigenvalues, it is roughly like a conic equation. And then you find the eigenvalues of the Hessian. And if they're both positive, then that means that it's a minimum. And if it's like they have opposite signs, they're like, it is like a saddle point. And if they have both are negative, then like the eigenvalues are both negative, it is like a local max. So but there are many things that actually these conic sections can be used for. So it's not just like, I mean, it's like kind of entertaining, but it actually has some useful application. But I think it's like a nice way to see that, these eigenvalues, eigenvectors are actually useful for something, because it may not have been clear from what we had done so far that they serve any purpose, except maybe for computing the exponential of the matrix, which is actually useful, again, if you take differential equations, for example. But this is like another, a different question where you can see the eigenvalues, eigenvectors being used for. Okay, so yeah, so this is roughly what I have to say in terms of the course material. So like officially we're done. So tomorrow, again, my plan is just whatever we can go over, any questions, any problems you're stuck on. So it's more like a review. So I won't do any new material. Okay, so yeah. So if you have any questions, you can come tomorrow. If not, I still, I will record the video. I just post it once it's ready. But yeah, I think it's a good place to end. So see you tomorrow if you want to ask me something.
So hi, Professor.
Sorry, yes.
Yeah, so I sent you the email and I saw you send me back. When will know the time for the other section of the final exam?
Do you mean the makeup?
Yeah, the makeup one.
Right. As I said, I'm not sure because I would have to check first, like, how many people end up needing to take it, but it wouldn't be this week. Yeah. Probably okay. Probably like most likely like next Monday or something like that. But that can be decided. I mean, it's like, the thing is like tomorrow's like, well, the final is on Wednesday, right? But what if someone has like an emergency on Wednesday, and then like they need to also take it? So I just rather wait until the exam has concluded to, to set up like a proper time. But yeah, it wouldn't be this week.
Okay.
I can tell you, yeah, just for you to know, to have like a good idea. Yeah.
Okay, got it. Thank you so much.
Yeah, no worries, no worries.
We have a good day.
You too, you too.
Mhm.